Okay, everyone, let's begin with section 1, Introduction to Application-Centric Infrastructure, Spine and Leaf Architecture. Okay, everyone, let's begin section 1 with the first topic in application-centric infrastructure, and that is the spine and leaf architecture. And you might be wondering, what is spine and leaf? I've heard this before. Well, data centers are changing, and they're changing for good. They're going from a 3-tier design architecture into a spinal leaf architecture, which provides more scalability, more redundancy, more performance for cloud and application intensive requirements. So if we need to scale up, we actually scale east and west. So we go left to right, and we keep growing our data center footprint by adding more leaves and more spines into our environment. We're going to take a look at the foundational aspect of the spinal leaf architecture, and we also are going to take a look at how the spinal leaf architecture helps us with solving all of our scalability and redundancy requirements that cloud environments and large-scale data centers require for today's access demands. Okay, and let's begin. So what I'm showing here on our video is a 3-tier architecture. This is a traditional 3-tier architecture design where we have our core layer. And on our core layer, we usually perform our layer 3 routing functions. Inter-VLAN routing happens at usually the core layer. So if you take a look at this topology here, our first layer is going to be the core. This is the upper layer. We have our distribution layer. And then finally, we have our access layer. Okay. If you have a VLAN, let's say VLAN 10, and VLAN 10 needs to communicate to VLAN 20, that is inter-VLAN traffic where it needs to hop on the core side or the core layer. And there should be a router or a switch that is performing layer 3 routing functions to communicate those two VLANs together. So let's say I'll draw this quick scenario here. So we have a machine. And by the way, this is the access layer. If you are familiar with the 3-tier architecture, on the core side, we got usually our cores performing layer 3 functions and connecting our distribution together. The distribution is connecting the core to the access layer. And this is how we expand in a 3-tier design. We connect more distribution switches. So let's say, for example, we decided to add another set of switches and we designate this to be another distribution switch. So what we do is we send an uplink to this, another uplink to there, because we're looking for redundancy. We want to make sure that I'm dual home to my core layer. If I lose one switch, or I should still communicate over the second switch. With that said, let me go ahead and clean this out. Usually our distribution layer is connecting our access to our core layer. So on our access layer, we usually have the IDF. This is where all my endpoints are going to be connected. And usually you'll have a stack switch, or you can also have a chassis switch on the access layer as well. We mentioned that we want to simulate how inter-VLAN traffic happens on a 3-tier design. So we have a machine here on VLAN 10, and then let's say that VLAN 20 is going to be red, and we have another machine here on VLAN 20. In order for me to communicate those two machines together, I have to route north, get to my core. And when we talk about a core, most of the time you're going to see an environment that is running HSRP or VRRP for redundancy purposes, where also GLBP is not as common as HSRP or VRRP is also a third option. So with HSRP, we usually have a single active core. The other one is a backup core. Let me explain real quick, and you should be aware if you're already on a CCNP level, you should know that in HSRP, we're going to have a dedicated address for the VLAN interface, right? So for VLAN 10, let's say we have 10.10.0.2, and then this is on core 1. Let's draw here core 1. And let's say on core 2, we created another SVI for VLAN 10 and then make another SVI here for VLAN 10, and this IP will be 10.10.0.3, and our virtual address, and this is the address that's gonna listen, or it's going to get those requests from the VLAN 10 endpoint. It's usually active in the core that is set as the master, or the core that has the highest priority in HSRP or VRRP. With that said, I send the traffic northbound, or I sent north, right? The core will see my request coming from VLAN 10, and then it's going to say, well, I see that you want to get to VLAN 20, which I do also have another interface on my core that knows how to get to that network. Let's say you got a VLAN 20, which is 10.20.0.3. You see where I'm going? 10.20.0.2, and then the virtual IP is 10.20.0.1, right? So with that said, your core 1, which is the active one, is going to send the traffic back down because now I know how to get to the VLAN 20 subnet. So it just hits the distribution side and the other side of the network. We have a distribution 1. We also have a distribution 2. And then we have, let's say, access 4. So we got 4 IDFs, and this is IDF 4, IDF 3, IDF 2, and finally IDF 1. So this machine on IDF 2 needs to communicate to this machine on IDF 4. However, they're not on the same VLAN. Because they're not on the same VLAN, I got to send my request to the core, and then the core will route down to my destination. Every single, I'm not going to say hop, because at this point it's just layer 2 all the way until I reach to the core. So my northbound communication hits the core, and I'm still just sending layer 2. So this whole layer right here from the core side to the access layer is all layer 2. So with that said, we have trunking on those links, and this is a multi-chassis ether channel where we have one logical switch, and then we have connectivity to both core switches. So this is all performed from a layer 2 perspective. We send the traffic in the core side, then it becomes a layer 3 where we are actually hopping into that VLAN 20 from my source, which in this case I am incoming from the core. The core hits the distribution 2. Distribution 2 will send the traffic down to my access, because now I know where that particular IP, the MAC address for this VLAN, is sitting on the network. The core actually knows about it. So the core basically knows how to forward that to the right destination. Here's the, I would say, the benefit of a spinal leaf topology where we are implementing either VXLAN or we're doing ACI. So this side of the network is all layer 3. This side of the network is all layer 3. Okay? The difference and the benefit of going layer 3, number 1, I don't need to worry about spanning tree loops because I don't need to port channel. I just do dedicated layer 3 links between my leaves, and we're going to go through the leaf and the spinal leaf discussion now, but all my connections between my leaf layer to my spine layer is all layer 3. Everything below is considered access. The disadvantage of a 3-tier design versus a spinal leaf architecture is that not only you have spanning tree as a factor, because everything is layer 2, as we mentioned, from the access layer to the core layer, everything is going to be sent in layer 2. Here's the situation. This is all broadcast, and as you know, broadcast, it causes a lot of quote noise, and this is where we do VLAN pruning, and then the VLAN pruning basically takes care of a little bit of jitter, but at the end, we still have a complex topology where if we're not cautious with the interfaces that we connect together, we can easily cause a loop and then spanning tree. Most of the time, we don't set spanning tree to be a specific ID on each switch. We just leave it as default, so it becomes a nightmare to maintain and to support. So with a layer 3 fabric like ACI, I would say 50% of my broadcasting, or even more than 50% of my broadcasting, it's basically gone, because at that point I am completely layer 3 end to end between my spinal leaf layers. So let's go ahead and take a look at that. So what we have here is a spinal leaf architecture. And in this case, let's focus on ACI. We have another flavor, which is VXLAN with BGP VPN, which is kind of not going to say that it's the same as ACI. However, the physical or the logical aspect of it, it kind of relates. It's kind of the same. Okay, so in ACI, we mentioned that our layer 3, that our connectivity between our leaf layer, and this will be our leaf layer, and then this will be our spine. The connectivity between the two, it's done from a layer 3 perspective. So in that case, let's say we have the same scenario where from ACI, we have our data center switches. And also, let's say we have IDF2. Okay, so we have IDF2 here, right? And IDF2 has a computer in VLAN 10, right? So we have a machine. This machine is on VLAN 10. And this machine, we mentioned that we need to communicate to a machine on IDF4. So let's say this is IDF4 right here. And we have a machine here on VLAN 20. In that case, what we do is, you remember, let's go back onto our previous slide. From the VLAN 10, I need to send everything is layer 2 until it hits the core, and then the core is layer 3 up down. So I am sending one hop layer 3 to the core, right? And then I am connecting back down to my access layer as my destination on VLAN 20. However, all my links up and down are layer 2, which means that I am allowing broadcasting anything from this network or from this side, from distribution 1 and access 1. Every broadcast is going to traverse all my links to distribution 2. So that's when your network might start having performance issues if you're not properly pruning the traffic that you need to prune, or allowing the VLANs that you need to allow on the chunks. So for example, you're allowing VLAN 10 from distribution 1 all the way to distribution 2, but that broadcast from distribution 2 will end in distribution 1, and the broadcast from distribution 1 will end in distribution 2, which then, like I said, it's a lot of noise. Not only that, you have the layer 2 loop possibility, where if you're not paying attention on your port channeling, you're not configuring it properly from a spanning tree perspective, you might end up in a spanning tree loop or a broadcast storm, which is very, very, very difficult to troubleshoot. So in a spinal leaf architecture, however, the difference is that my machine on VLAN 10 goes upstream, right, to my ACI leaf, and let's say this is a leaf 1. So we're going to write this here, leaf 1, and let's say here is leaf 4. So from here, you remember on our 3-tier, we jump on the core, and then the core sends the traffic back down. In this case, it's a east-west traffic flow. So let's say east-west, west-east. So we're going left to right, right to left. Basically, we can go either this way, back to leaf 1 for leaf 4, or leaf 1 to leaf 4. So it's an east to west traffic flow. And this is where we see our east-west traffic flow versus our north-south traffic flow. North-south, we go up to the core and back down. So we're going north to the core, back down to my destination. In a spinal leaf east-west traffic flow, we go east, or in this case, I can go west from the leaf east to the destination. Please follow me here. VLAN 10 goes up to its closest leaf. You remember in 3-tier, we only have one active core. In a spinal leaf topology, we have cores duplicated across all my leaves. So this leaf can do the same routing functions as this leaf, and finally as this leaf. So I don't need to send all the traffic to a particular destination, which then creates another issue. It might saturate that connection upstream or northbound to my core side. Or I can send my request to my closest leaf, and from there, it will be forwarded to the right destination. So my VLAN 10 wants to communicate to VLAN 20, hits leaf 1. Leaf 1 sends the traffic up to the spines, and the spine will reflect the traffic down onto the destination. The spines, you might say, oh, those are the cores. They might look like the core because we're used to see that 3-tier architecture. However, the spines are there just to aggregate traffic. They're not there to do routing for your client traffic or for your virtual or your tenant networks. And we're going to go and discuss tenant in another video. The spines are there just to reflect the traffic and aggregate. All my links in ACI are going to be used at the same time. We're doing equal cost multipathing. So from leaf 1, we were just saying VLAN 10 hits the closest spine, or it decides I can go over spine 1, I can go over spine 2. It doesn't matter because I am equal cost. I can use either 1 or 2, which also brings another benefit. We are having line rate load balancing here because I am actually able to send traffic both ways to both spines and to the same destination via 2 different links. So there's only 2 hops away from my source and destination. 1 hop going to the spine, 1 hop going back down to the leaf. So we know that our traffic is predictable. We know the path that the traffic is going to take. Versus in the core, we don't know which interface or which link on the port channel it went. It just went upstream, and we just know that the traffic got there because either we are able to ping or we're able to hit a web service. So we know that it's working, but we're not able to predict if, for example, the traffic from this switch went this way or went this way. It's just LACP. It's taking care of the hashing. It's sending it both ways. And also here, I don't know if the traffic hit there or hit the other side. So that's where ACI brings a benefit over a traditional 3-tier architecture. You have predictable traffic flow. You know exactly where the traffic is going. You know that it's east to west, and it's not going to go crazy over a layer 2 link. It's just going to go with a dedicated layer 3 link. It's going to go up to the spine, and it's going to go back down to the leaf, and it's going to get to my destination. So let's say this machine, there's another machine here on VLAN 20, and wants to communicate to this machine in VLAN 10. So in this case, the same. Either I can go over spine 2, and spine 2 will reflect me back down to my destination leaf. Okay? This is actually doing my quote routing. My core switch function, it's my closest leaf. So I am aggregating and I am giving some sort of load balancing to the routing process, because with this in place, I am routing using my closest leaf. So all my leaves are actually routing my user traffic, which brings a lot of scalability. So let's say, let me go ahead and draw real quick. I'm going to draw a very, very simple spinal leaf diagram so you can understand a little bit more. So let's go ahead and draw the 2, 3, and 4 leaves, right? Let's go ahead and connect those leaves together via the spines. You know what? I'm going to go ahead and label this spine 1, spine 2, leaf 1, leaf 2, leaf 3, and leaf 4. Right? So let's go ahead and make some connections. So I'm going to leave it in black. So we mentioned that we have equal cost path to spine 1 and to spine 2. We can use either one of the 2 destination spines to get down to my destination leaf. Obviously, we want redundancy. If I lose spine 1, I need to have another link going via spine 2. I can either use this link right here. I can use this link going up to the spine 1, or we can use another link going to spine 2. If I lost this spine 1, I still have spine 2. Okay, so let me go ahead and finish connecting the fabric together. So let me throw another wire, another uplink to spine 1 here from leaf 2, another uplink to spine 2, do the same thing for leaf 3, and finally do the same thing for leaf 4. Okay, so with this, I know, like we mentioned, we have east-west traffic flow. I have a machine here. This machine needs to talk to a machine here. Very simple. Like we mentioned, 1 hop to the spine, 1 hop down to the leaf. This is predictable traffic. We know exactly where the traffic will go in order for me to know the destination. So this is the basics in a spinal leaf architecture. Like we mentioned, east-west traffic flow is predictable. It's fully aggregated. All those links are layer 3. You're going to take advantage of all those links versus in a 3-tier design where you might have spanning tree blocking a redundant link Or you might have limitations with port channeling, where this is literally a layer 3 link. Everything will be forwarded equally. On the next video, I am going to discuss the policy-driven architecture. How does ACI makes the magic happen? How will ACI define how your network is going to behave? What are policies? What are endpoint groups? What are contracts, tenants, everything? We're going to discuss that in our next video. Okay, everyone, in our next video, we're going to take a look at ACI Fabric components. Thank you for watching.